Ladies and gentlemen, welcome back. This is the second lecture of my e-learning course called Equilibria of Materials, or the Basics of Calphad. Today, let me discuss a rational system of quantities and units, which is, unfortunately, not the same as the SI system of units. In the previous lecture, we discussed that without a system of quantities and units, it is not possible to discuss natural sciences and engineering. So that is why let me first discuss quantities. In the long history of mankind, different groups of people developed in long separation different cultures, languages, religions and habits, including how to measure different things. Obviously, these led historically to chaos, and this was of course understood by the best minds of science, who suggested a solution to select so-called base quantities from all possible quantities. Now, what are our requirements to those base quantities? First of all, they should be as simple as possible to make sure everyone understands them exactly. Second, the number of those base quantities should be as small as possible to make sure everyone can remember them with the highest chance. Third, those base quantities should be independent each other, and finally, those base quantities should be selected such that any other quantity can be derived from them. It was probably Max Planck in 1899 who first came up with a reasonable system of base quantities, although he has been working on the development of quantum mechanics. But you know, whatever is good as a system of quantities for quantum mechanics, it is probably equally good for material science, engineering, or even other scientific fields. So the 5 base quantities of Planck were length, mass, time, temperature, electric charge. Today, in the SI system of units, for those quantities the following units are used: meter, kilogram, second, Kelvin and Coulomb. And I also mention here the symbols of those quantities, which are usually the first letters of the English names of those quantities: capital L for length, M for mass, T for time, capital T for temperature, and Q for electric charge. Well, yes, there is no Q in electric charge, but when the science of electromagnetic phenomena started, then charge was not called a charge, it was rather called a quantity of electricity, and that is how Q comes from quantity. Okay. Unfortunately, in 1960, when the SI system of unit was created, this paper of Planck was kind of forgotten, lost, or ignored, or I don't know, but this is the reason why recently I was forced to publish a paper on the comparison of the system of Planck to the SI system, which will be discussed later, and of course showed that, well, the Planck system is much better. Now, I should mention that this paper is published not in the best, most suitable journal for this subject, because that journal would be Metrologia, which is the official journal of the SI system of units, but unfortunately Metrologia simply rejected my paper. I will come back to this question later. Now, considering base quantities, we might also think of our friends economists, who might need their own base quantity called obviously money, and maybe measured USD, United States dollars. But now let me explain how we use this quantity and unit. Now obviously we are going to count $1, $2, $3, meaning we are going to use positive integer numbers long ago discovered by mathematics. That is why, in fact, I'm sorry, but we don't need such a new quantity or such a new unit. This is equally true for all countable things. whatever you can count using positive integer numbers, then you don't really need a new quantity or unit. And this is, by the way, true also for atoms, which are also countable. We will discuss this question later. But now let me explain how, in the easiest way, you can create derived quantities based, of course, on the base quantities. The easiest way is to multiply or divide base quantities to the given power. For example, velocity is defined as meter per second, so this is the path done within the given interval of time. Acceleration is the increase in velocity per given time interval, meter per second square. Force is the multiplication of mass to acceleration, kilogram times meter per second square. You see, this is such a too difficult unit that it was reasonable to create its shorter name called Newton, obviously after the famous Isaac Newton. And now we usually use Newton as a unit of force, but everyone should remember that this Newton is fully identical to kilogram meter per second square. Energy is created as a multiplication of force by the path. For example, if I apply a force to my chair and I successfully push it to the given path from the left corner of my room to the right corner of my room, then I perform work measured in newtons per time meter, or joule, which is nothing else as the energy applied on my chair. Now, this energy and joule are the quantity and the unit which I will use very frequently during this course of Equilibria of Materials. Power is nothing else as the amount of created energy per time needed for its creation, measured in joule per second, watts. If watts are multiplied back by seconds, then obviously you get back joules, which is energy. This is also true if you multiply back not by seconds but by another unit of time, such as hour, and even if you multiply this by 1000, or even if you apply the prefix kilo, meaning 1000, so this leads to the well-known unit of kilowatt hours. And now you understand why is it energy, being not equal but proportional to joules. Surface area is measured as square of length, and pressure is measured as force divided by surface area, Newton per square meter, or pascals. Let me mention that pressure is reasonable to calculate only if this force acts perpendicular to that surface area, and also if this force is evenly distributed along that surface area. In this room today, the air pressure is approximately 10 to the power 5 pascals, which is 1 bar, and that 1 bar will be the standard pressure in this course. But now let me explain to you that multiplying and dividing by each other base quantities is not the only way to create derived quantities. Actually, any mathematical function can be used for both the base units or derived units to create another derived quantity or unit. As an example, let me show to you pH. But first, let me define volume as a cube of length and some concentration unit, molarity, in mole per cubic decimeter. So, if we take the molarity of hydrogen ions in aqueous solutions and take a negative logarithm of that, then we get pH. You see now, logarithm is used on one of the derived units, and cosine and any other mathematical function can be equally used. You know, chemists know well that in neutral water the molarity of hydrogen ions is 10 to the power minus 7 mole per cubic decimeter. If you take the 10th logarithm of 10 to the power minus 7, you get minus 7. If you take a negative of that, you get 7, and this is how the pH of neutral water becomes 7. Let me mention that I don't really like this unit of concentration, molarity, and this is because it depends on pressure and temperature. and this is because the volume of the solution depends on pressure temperature. This is really not convenient for this course, and that is why in this course I will use another concentration unit, atom by atom, atom divided by atom, or mole divided by mole, which will be independent of pressure and temperature. Okay, ladies and gentlemen, so after what was said, we could finish this lecture because we have the 5 base quantities. But in 1960, the SI system of units was created, established. Let me show its beautiful and colorful logo. And let me show to you the essence of the SI. They claim they have, or we have, 7 base units and 7 base quantities. The good news is that the first 4 are the same as in the system of Max Planck. But the bad news is that we have a contradiction here, because 7 is obviously not 5. Let me explain that the SI system of unit was created, by the way, for the big taxpayers' money, not to create a problem. Just the opposite. It was created to resolve a real international problem with the big chaos in measurements and units which existed before. And the good news is that the SI offered a solution, and the good news is that this solution was accepted internationally, and then we have today the international system of measurements and units, and this is good. What is not good at all, what kind of system we have today. Now, let me explain step by step. So as I said, I have no problems with the first 4 choices because they coincide with that of Max Planck. Let me look at choice number 5, electric current according to the SI system, electric charge according to Max Planck. Well, they both are good enough at the first sight for electromagnetic phenomena. And the big question is which of them is a real base quantity, which of them is more simple. Now, talking about simplicity, I cannot make electric charge more simple. I cannot divide it into smaller, more simple things. But thinking of electric current, it is easy to do, because electric current is nothing else as electric charge divided by time. By the way, that's why it's called a current. It means a flow of charges which flow, and per unit of time, so they have a certain velocity. So electric current, amperes, means nothing else as a velocity, a flow or current of electric charges in the unit of coulomb per second. So, which one is the real base quantity? Of course the charge. And which one is the obvious derived quantity? Of course the current. So, dear SI bosses, I hope you are listening to me. Please vote again and put electric current from the current box of base quantities into the box of derived quantities. And because today you keep electric charge in the wrong box of derived quantities, please put it to the right box of base quantities. As you understand, it will not influence the meaning of amperes or the meaning of coulombs. You can still use all those electromagnetic quantities exactly in the same way. What is changed? What is changed is teaching, is understanding, that we call base what is a base, and we call derived what is derived quantity. Now let me, by the way, make it maybe more clear by a small and maybe a little bit stupid example how I could spoil the system if I wanted, similarly as the system of Planck is now spoiled by the SI system of unit. Okay, length and time are obviously base quantities. I guess everyone agrees with that. I agree. The SI system agrees. Max Planck agreed. Fine. But let me put length and time for a moment into the box of derived quantities, and let me take from that box velocity and acceleration and put them here into the box of base quantities. This is velocity, meter per second, acceleration, meter per second square. I hope everyone can clearly see that mathematically, using meter per second and using meter per second square, it is easy to create or define both meter and second. So mathematically, it is perfect. But is it perfect according to our natural understanding? Of course it is not. Of course it is clear for all of us that length and time are the fundamental and independent quantities, and velocity and acceleration are just derived quantities from those two fundamental things, length and time. Equally, as what is fundamental in electromagnetic phenomena is electric charge, and what is one of those derived quantities is electric current. Okay, now let me discuss a little bit the sixth so-called base quantity of the SI system, which is the luminous intensity measured in candela. It means how much light is given by one candle. More scientifically, it means the energy of photons of given frequency reaching our eyes per unit time under unit solid angle. Okay, wait a minute. So the SI system of unit calls a quantity, luminous intensity, a base quantity, and defines it through a derived quantity energy, another derived quantity frequency, the third derived quantity solid angle, and through a base quantity time. How is it? Come on. Isn't it clear that a base quantity must be independent of all other base quantities and of course independent of all derived quantities? Well, I hope it is clear, and if it's so, then it's also clear that luminous intensity is a typical derived quantity. Dear SI bosses, no problem, please sit down, vote again, put luminous intensity from the box of base quantities to the right box of derived quantities, and you can use candela as you like, exactly in the same way. Just clear our teaching, clear our understanding. Well, similar thing I can say about the seventh so-called base quantity of the SI unit, and is the amount of matter, mole. The strange thing is that it was actually put into this box only in 1974, so it's hard to imagine how the SI system could exist between 1960 till 1974 only with six quantities, base quantities. Well, obviously they could exist because the amount of matter is in fact not a base quantity, which I will show very soon. So, what is the amount of matter about? It is about the Kondo atoms. Well, Kondo atoms because materials are made of atoms, and that's why we're counting atoms, because they are countable. So how we do that? 1 atom, 2 atoms, 3 atoms, 4 atoms, etc. Exactly as we are counting the US dollars, $1, $2, etc. What we need for that? For that we need only the positive integer numbers of mathematics, and we don't need at all a new quantity and a new unit, especially not a base quantity and a base unit. Well, I can accept if you want to explain to me that the atoms are so small, we need a huge number of them to get enough material which is measurable by the engineer, and that is why it is worth grouping the atoms, create a group called mole. Fine with me. And then also I can accept that the number of atoms in such a group called mole can be called the Avogadro number. No problem with me. But at this point I should say that this Avogadro number, which is the number of atoms in the group called mole, its number is an arbitrary choice. Equally arbitrary as 12 was an arbitrary choice when dozen was created. Okay? Well, now dozen is fixed, of course, but when it was created it could be anything else. Now, Avogadro number is fixed, of course, but when it was created not that long time ago, in 1974, it could be selected in a more clever way. Which way? Well, first of all, it should be a positive integer number because it is for the number of atoms in 1 mole. Okay. Second, well, please select it a 1-digit number because it is arbitrary and because me, international professor, and you, international student, can much more easily remember 1-digit numbers compared to 9-digit numbers, which follow soon. And there is one more point with the Avogadro number. It is actually connected with the molar masses, which we define later as gram per mole. And those molar masses existed since the 19th century. In a way, they were called relative atomic masses. For example, the lightest atom, for the lightest atom hydrogen, this relative atomic mass was arbitrarily selected 1, just because it was the lightest one, per some amount of matter not really defined, but taken as constant. And then compared to this, the relative atomic mass of carbon appeared to be 12 in the same unit, and for oxygen it appeared 16 in the same unit. In other words, since the 19th century it was known that the carbon atom is 12 times more heavy than the hydrogen atom, and the oxygen atom is 16 times more heavy than the hydrogen atom. Now that, ladies and gentlemen, was a great discovery in the 19th century, and well, actually then we can say that since like 1860 chemistry became really scientific. It could really measure properly things, and based on that, very soon in 1869 the periodic table of Mendeleev was created. We will discuss that all later. But now let me come back to the Avogadro number. So we are searching for a number which should be, if possible, a 1-digit number and should satisfy our need that if the molar mass is expressed in gram per mole, then hydrogen should have a molar mass of 1 gram per mole, carbon 12 grams per mole, and oxygen 16 grams per mole, of course approximately, rounded at least to the integers. Well, ladies and gentlemen, this is a very lucky situation, because we have such a 1-digit number, and this is 6 times 10 to the power 23 1 per mole, which satisfies all what was said before. And this 6 is actually 6.0, so it's not 5.9, it's not 6.1, no, it's 6.0 10 to the power 23 1 per mole. That's great, that's great, let's use it. But you know, if we explain to people in the SI system committee meeting that we have this number which is similar to the number 12 in a dozen, and this number is actually half dozen times 10 to the power 23 atoms in 1 mole, then everyone will say, perfect, it is so simple, fine, do it, but why you want to call it a base amount and the base unit? Come on, it would be too transparent. But the chemist wanted to have their own unit, base unit and base quantity, as I understand today, because I am just surprised how this choice was made in 1974. So I suppose they wanted it to make it scientific looking. So that's why they overcomplicated everything. How they did it? They said, let us define the Avogadro number as the number of atoms in exactly 12 grams of C12 isotope. C is for carbon, 12 is the number of protons and neutrons in the nucleus of one C12 isotope. Okay, what was the consequence? Ladies and gentlemen, the consequence is this 9-digit number, 6.02214076 times 10 to the power 23 1 per mole. Well, try to remember, because you must remember. And this is only different from a 1-digit version by 0.4%. And of course, from both you get the same integer result for all these 3 numbers. So why is it better? Well, it is only better because in this way they made the system so complicated, and that's why scientific looking, that the politicians who were voting here in the great committee meeting of the SI in 1974 or before, they actually voted yes. Congratulations. As a result, now everyone must remember this 9-digit number. Thank you so much. You know what could be, so what is instead? Well, instead you can be lucky that at least C12 has an integer 12, exactly 12 gram per mole molar mass by definition. But who cares? I mean, we have hundreds of isotopes. The molar masses of those hundreds of isotopes are tabulated. They are all around 9 digits of accuracy measured. In the same way, C12 could be tabulated with 9 digits and have the integer for the Avogadro number really to remember for each school boy and school girl and each professor. But I have to tell you, now it's too late, of course, because in 1974 it was decided like this, and since then everything which is a molar quantity was tabulated based on that, so we cannot change that today because we don't want confusion. Fine. Let me, by the way, also mention that this strange choice of 12 gram of C12 seems to be clever, because in this way the number of protons and neutrons are the same, so the masses are kind of averaged, because later we will see that the masses of protons and neutrons are a little bit different, so this averaging might have sense, but only if the ratio of neutrons to protons in each atom and isotope is the same and equals exactly 1. But this is not the case. In fact, as I will show later, this ratio between the number of neutrons per protons per atom is anything between 1 and 1.5. And that is why this strange definition doesn't help us at all. Okay, but let me come back to the basic question. Is the amount of matter a base quantity? Of course it is not, because it is based on an arbitrary definition of an arbitrary number. So please, dear SI bosses, I hope you are listening to me. Please put the amount of matter to the box of arbitrary quantities and put them all into box of arbitrary units. Don't worry, no problem, we can use them exactly as we use them today. I personally promise I will use them during this course, no problem, just clear the box of base quantities from anything which is not a base quantity, please. And if you talk the next time about the Avogadro number, I know you like to call it the greatest constant in nature, but please understand, it is not. It is just an arbitrary number. Well, yes, such a difficult arbitrary number, but it is an arbitrary number because it is based on this arbitrary choice of 12 grams of C12. Right. So summarizing, the SI is a political system which makes decisions by voting, and you know, no real science can be decided by voting. Moreover, SI makes the results of its voting a law, which is obligatory for all the citizens of all the countries who are parts of this agreement. Now Hungary, my country, is part of this SI agreement, which is, by the way, a good thing because we are part of the international agreement. What is bad about it? That what kind of agreement was created? Okay, and because it's a law in Hungary, and because I am the citizen of Hungary, that is why this law is obligatory to me. And nevertheless, dear international students, I am not teaching it to you. Why? Because I follow Descartes, the French philosopher, who said, a scientist or a professor is a scientist or a professor only if he or she follows his or her own mind and judgment. Anyone says anything, we should let it through our mind, make it clear for ourselves. Is it true or not? Is it Good or bad? Is it the scientific truth or not the scientific truth? Now, ladies and gentlemen, I am teaching to you the best scientific truth to my best knowledge. Okay, I am not teaching to you what I learned myself 40 years ago in school. I am not teaching to you what law it is telling me to teach. No, I am teaching to you the best I know. This is the way how I try to serve you. Now in this box I'm using a little bit of offending language like the SI bosses are cheating us, etc. But why I'm saying so? My students can tell me, Professor, wait a minute, take it easy. I mean, the poor SI bosses are probably only making little mistakes, so why don't you help them? Why don't you write a little letter or paper explaining them the truth? So why don't you do that? Oh my dear students, yes, exactly the same naive I was 10 years ago when I wrote my paper about the comparison of the system of Planck and the system of SI. I submitted it to the official journal of SI called Metrologia, and as I mentioned before, it was rejected. The problem is not that it was rejected, because my papers are rejected like 5 times before they are actually accepted in the 6th journal. No, the problem is why my paper was rejected. The editor of the Metrologia journal, who is one of the SI bosses, explained to me, your paper is rejected because what you claim is obvious, and the journal never publishes obvious things. Okay. The last part of the sentence, I agree. The journals, the best journals, should never publish obvious things. But the first part of your sentence, dear SI boss, that all my claims which I made right here during the last 10-20 minutes are obvious, it means that it's obvious for you at least. It means that you know that you, the SI system of unit, are cheating the world. You are cheating the world knowingly, and you are paid by the taxpayers' money. Oh, come on. Think again. We have 7-8 billion people in the world. We can reach about 70-80 years of age, at least in the times of coronavirus. Divide the two numbers, you get 100 million, meaning 100 million young people are passing through the educational system of the world annually, and they probably have 1 million of teachers. Suppose those millions of teachers don't follow Descartes, suppose they are obeying the law, and then it means million of teachers cheating 100 millions of students worldwide annually, and that's because the SI system is cheating those teachers. What is the reason? Maybe I am still too naive, but I don't understand. You know, I like understanding things. By the way, that is why I do not watch political things on TV for many years, but please, at least in natural sciences, in which I am a professor, at least in the basics of natural sciences, which is the system of quantities and units, let me see things properly. And you know what is the problem? The SI is telling us we have 7 base quantities, so anyone can think the world, the nature is 7-dimensional, so we should observe it as such, we should model it as such. But after Planck, in my best understanding, nature is only 5-dimensional because it has only 5 base quantities. And it is much more simple to observe the world like this, it's much more simple to model nature like this, and remember the subject, Equilibria of Materials, is actually modeling materials. By the way, my PhD student Adam Weg, after listening to me several times the same story about 5 versus 7 base quantities, asked me, okay sir, but why 5? Why not 4? What if I prove to you that 4 is enough and the 5th one can be derived from the first 4? I said, Adam, if you do it, you get a Nobel Prize. I mean, not from me, but I kind of promise to you, because that would be a great discovery. But while Adam is doing on this problem and searching for his proof, please SI bosses, dear SI bosses, please listen to me. Go back to basics of Max Planck 1899. After the coronavirus is gone, sit down again, vote and say these 5 are the 5 base quantities. Thank you so much in the names of all my students in advance. Well, the development of the SI system of units is going on. In 2019 they introduced a big change. You see, they are developing it, although not into the right direction. I mean, at least not to the direction I am asking for. But now let me tell you what kind of development is done in 2019. The SI selected 7 so-called base constants, meaning we have lots of constants in nature, so they selected 7 of them and fixed their values forever. So this is the list of those constants, the symbols and the fixed values and the units. And the claim is that after these 7 base constants are fixed, we should find the meaning of each base unit which they have from this table. And the constants are positioned in a logical way, because the first one contains only second, so from these I can understand how much is 1 second. Then from the second one, if I understand already how much is 1 second, I can gain the knowledge about the meter. From the third one, joule is involved, but you remember it's kilogram meter square per second square, so kilogram is only new here. So if I know already what is second and what is meter, then from the third one, from the Planck constant, I can understand how much is a kilogram. Then from Coulomb I can understand how much is the ampere. Then from the fifth one I can get the knowledge about the Kelvin, and then from the Avogadro constant, of course, the mole. And finally, in a little bit difficult way, but using these reorganizations here, we can understand how much is 1 candela. So this is a new system of the SI base constants. Let me come back maybe to the choice of elementary charge. By the way, this is a perfect choice for me. I fully agree that elementary charge was selected as one of the base constants, and that is why one of the base constants is measured in Coulomb. Now the only funny thing is that at the same time the SI system keeps Coulomb as a derived unit. So now they provide the base constant in the derived unit, which is quite funny. Because what shall we do now? Using Coulomb and second, combining them, we should derive for ourselves the base unit of the SI ampere, and then if later we are interested, okay, how much can be one of the derived units such as Coulomb, then we should multiply back by seconds the ampere and get the Coulomb again. Isn't it a little bit too difficult, dear SI bosses? I mean, once you did that choice, which is a very good choice, so why you don't listen to me, and why you don't change by places electric charge and electric current, making electric charge the base quantity and Coulomb a base unit? Well, I don't understand. I would say I still don't understand. But let me use this chance to introduce 2 constants which I'm going to use in this course. The first one is the gas constant, which is the multiplication of the Boltzmann constant by the Avogadro number. It is approximately 8.314 joule per mole Kelvin. We are going to use it a lot during this course. And the second molar constant is the Faraday constant, which is the multiplication of this elementary charge by the Avogadro number, providing 96,485, etc. coulomb per mole. Okay, now let me show to you why the SI thinks this new system is better than the old one. First of all, you should understand that so far the meter and the kilogram was based on étalons kept in Paris, and that was of course a kind of dangerous thing, because those artifacts were obviously corroding, meaning both meter and kilogram were changing in time. Second, it was always a danger that they can be lost, they can be stolen, etc., etc., etc. And after these constants are introduced, now the meter and the kilogram are safe, because these numbers are not corroding, cannot be lost, and cannot be stolen. So it is indeed an elegant solution from the SI system. Well, it's also good news that of course these fixed constants are selected such that the meter back in 2018 is the same meter in 2020, because the constants were selected such. Okay, it's a good news. Then they also claim that based on this, nobody needs anymore the étalons kept in Paris, because it was of course hard to get access to it. Anyone, anytime, anywhere can reproduce the constants. And maybe a little bit funny claim that using this table we can communicate better with the aliens, just in case if we meet them, because suppose the Martians come here, now if they come here probably they understand how much is the speed of light, and then based on the speed of light we can make good friends with them. Okay, now let me announce some of my doubts, but remember only after Descartes. Okay, so I'm just imagining myself in my home. I have 4 grandchildren already, so one of them is asking me, "Grandpa, can you please explain to me how much is 1 meter?" Okay, I mean 2 years ago what I would take, I just take a ruler 20 centimeters long, plastic, very cheap, which I keep at home, and then explain very easily how much is 1 meter to my grandson. But after 2019, what shall I do in the kitchen of my home? So first of all, I take out some of the cesium of my pocket and measure its hyperfine transition frequency. On the other hand, I also take from my another pocket some vacuum, which of course I keep there just in case, and measure the speed of light in vacuum. And then after these 2 measurements are done quickly, efficiently in my kitchen, I combine the measured results with these numbers in a way that my grandson understands everything efficiently. Okay, well, good luck to you all, mothers, fathers and grandparents, because you should realize this is how you should explain to your grandson how much is 1 meter. Right. Now, more seriously speaking, the development of science doesn't stop only because the SI system was so nice to fix all these values. So young people are probably measuring even today in the best laboratories of the world the speed of light in vacuum. And suppose they want to publish their result, which is new and which they believe is much better than it was before. So what they can do? Well, actually it's very difficult for them to publish their result, because the speed of light in vacuum is fixed by law. So how they publish, how they show they found something new? Well, the only thing they can say, okay, because the speed of light in vacuum is fixed, what I can say that now, based on my measurements, the meaning of seconds or the meaning of meters is now shifted. Well, it's kind of dangerous. And also remember that each lab around the globe is equipped differently. Some of Hungarian labs are equipped from 1,000,000 forints or so. Some of other labs in the rich countries are equipped from billions of US dollars. Now, much probably the value of the speed of light in vacuum measured in these two labs are different. And what is the consequence? They are different according to measurement, but they are fixed according to the law. So what the scientists are doing in the two different labs? Well, they are shifting the meaning of meter or the meaning of the second in their labs. Well, which one to shift they can decide by measuring also the hyperfine transition frequency of cesium, no problem. Okay, and what is the consequence? The consequence is that the meaning of 1 meter and the meaning of 1 second and the meaning of everything else is now will be different in each laboratory, which dares to measure all those 7 base constants. And that goes against the basic principle of the SI system. Remember, the SI system of units was created in 1960 to resolve a great international problem, which was the chaos in measurements and units and in understanding how much is 1 meter. Now I'm afraid we are, by fixing those constants, we are coming back to this chaos, because after that in each laboratory, if each of them separately measure these constants and compare the measurement to the fixed values, they will be working with different meters, etc. But of course, the SI bosses can tell me that at this point maybe I'm not right, because the artifacts kept in Paris for meter and kilogram are corroding much more than the expected inaccuracy between the measured values in different laboratories around the world. Well, they even might be right in that. Now, coming back to Alliance, let me mention that this will work only if first we find a common language with them. But for this purpose, I prepared detailed instructions for the Martians. They appear here. Suppose the Martians are interested how much is 1 second, 1 human second. But for that, they obviously already understand what is time, and they also measure their time, and for that they have their own unit of Martian seconds. If so, what they should do? They should measure the hyperfine transition of cesium. Suppose they got this value of 5.240 10 to the power 8 1 per Martian second. Now, if the measurement is correct, and well, probably it is correct, then they should make this result equal to the fixed value by the SI, which is 9,192,631,770 1 per human second. And from this comparison, they can finally find that 1 human second equals 17.54 Martian seconds. Well, of course, supposing that it is really what they measured. Well, it is doable. Thank you. Now, what if the Martians are also interested how much is a human meter? Now, then probably they understand what is length, and then probably they already have the Martian meter. So, what they should do, they should measure the speed of light, of course in the Martian vacuum. Suppose they got the value 8.272 10 to the power 7 Martian meter per Martian second. Then first, using the both coefficient between human seconds and Martian seconds, they should convert it to 1.451 10 to the power 9 Martian meter per human second. And then this value should equal the fixed value by the SI, which is 299,792,458 meter per second. And from this comparison, of course, the human second falls out and meter remains, and then 1 human meter appears to be 4.840 Martian meter, of course supposing this is really what they measured. And so on if they want to go on. Well, it is all doable. My bad news is, by the way, ladies and gentlemen, my dear international students, this is not only instructions for Martians. This is, by the way, instructions for you, my dear international students. So please be prepared. You should find how much is second and meter according to the SI system of unit since 2019, exactly in the same way. Good luck! Let me now speak a little bit about the prefixes of the SI system of units, which is a very good system. Prefixes are put in front of the units, and prefixes replace difficult sayings such as 10 to the power 9, etc. Instead of that, you can say giga and use the symbol capital G. For example, if you measure a mechanical property of material and it is 5 times 10 to the power 9 pascals, then instead of that you can say 5 gigapascals, which is indeed easier. Or suppose you measure length, which is 5 times 10 to the power minus 9 meters. Instead of that you can say the length is 5 nanometers, which is again easy. By the way, I work in nanomaterials. I define them as materials having at least one phase with at least one of its dimensions below 100 nanometers. And again, in this definition, I say 100 nanometers, which is much easier to me compared to saying 10 to the power minus 7 meters. Well, perfect. But again, the SI system created a problematic trick here, because they selected as a base unit for mass not gram but kilogram, so they are confusing the real unit with the prefix. Because kilo only means 1000, we use it frequently, so instead of saying today I walked 5 times 10 to the power 3 meters, I can say I walked 5 kilometers, which is reasonable. By the way, the meaning is not changed, because instead of saying the mass of something is 5 times 10 to the power 3 grams, you can say the mass is 5 kilograms. So this is fine. The kilo in kilogram kept its meaning 1000. But then you can ask, okay, Professor, why then you say it's confusing? Now this is because we have a very important rule in the SI system of units, which is really very useful. Let me teach to you that. So the rule says that if quantities with SI units and no prefix are multiplied, divided, etc. in any way, then you always get as a result another quantity in SI unit also with no prefix. Well, exception if you obtain as a result a mass, because that mass will be obtained in kilogram, and kilo is obviously a prefix, but because kilogram is the official base unit of mass, kilo is not really considered here a prefix. The same story if you want to substitute mass into the equation, and then the rule says you should substitute with no prefix, but please be careful. If you substitute mass, you must substitute it in kilograms, because kilo here is not really considered as a prefix, because it is the official base unit of mass. Well, to add to the confusion, even if kilogram is considered to be an official base unit of mass, it doesn't mean that other prefixes are added to kilogram. So you never say millikilogram, you say only milligram. You know, milli means 10 to the power minus 3, so milligram is obviously 1000 times less than a gram, and you say milligram, and you mean 1 million times less than a kilogram. But please don't say millikilogram, which would follow from the previous sentences. Well, we cannot change that anymore. Mass is defined and kilogram is defined like this. Let's live with it. Okay, ladies and gentlemen, this lecture is almost finished. But of course I realized that it was too long. I guess you never imagined I can speak that much about the system of quantities and units, especially if I claim that we have only 5 of base quantities. But you know, we have this strange SI system, so of course, because this is a law, I must have been discussing this as well. Now, so many things have been said, that is why I think a summary must be given here. So first of all, after Max Planck, I still claim that in nature we have 5 base quantities, which is the length, the mass, the time, the temperature, and the electric charge. However, compared to the existing SI system of units, there are consequences, if I think so. And the consequences are that electric current should be a derived quantity and not a base quantity. And its unit ampere should be a derived unit and not a base unit. Logically, electric charge should be a base quantity and not a derived quantity, and its unit coulomb should be a base unit and not a derived unit. Also, luminous intensity should be a derived quantity and not a base quantity, and its unit candela should be a derived unit and not a base unit. Finally, the amount of matter should be an arbitrary quantity and not a base quantity, while its unit mole should be an arbitrary unit and not a base unit. And of course, as a consequence, the Avogadro number should be considered as an arbitrary number and not as the greatest constant of nature. Now let me mention that if these changes suggested here are introduced, it doesn't make any confusion for the user, because the ampere, the coulomb, the candela, and the mole can be and should be used exactly in the same way as you use them today. It is only needed, these changes, to make the picture clear, to have a transparent view on nature, and to make us able to model nature and natural phenomena in a more efficient way, and of course to teach the students in a more efficient way. Now, further, to make absolutely clear what I suggest, although I have been discussing 2 other things, but I must stress they should not be changed to avoid confusion. So although it would be really nice to have the Avogadro number, 1-digit number, exactly 6 times 10 to the power 23 1 per mole, but it's too late. Unfortunately, we must keep the SI value 6.022 whatever times 10 to the power 23 1 per mole to avoid confusion. Second, it would be really nice not to confuse prefixes with units and to have gram as a base unit of mass, but it's too late now. The SI selected kilogram as a base unit of mass, and we must keep with that to avoid confusions. Before ending this second lecture, let me spend a couple of minutes on some philosophical questions on the development of science, including, of course, the field of base quantities. When science was started, we had the first philosopher, and he or she was obviously sitting lonely and thinking about everything at the same time. Now that was surely the unified science. But then more and more people were involved into doing science. They were searching and finding new paths, new interesting subjects to study, and therefore sub-disciplines were separated, and this is how natural philosophy was separated from the arts and social sciences. By the way, natural philosophy is just the old name for the same natural sciences. And later, even within natural philosophy, physics, chemistry, biology, material science, etc. separated, and this process seems to be endless. We have deeper and deeper specialists in each subfield. However, maybe this tendency is not the best one, because at the end of the day we end up with knowing more and more and more about less and less and less. So there also exists another trend in science, and this is to reintegrate science into a single formula or a single principle. Now let me share with you my single principle, and this is I call the double principle of minimum energy. You will see it's not really mine because I'm just combining two existing principles. Let me start with the Equilibrium of Materials, this course. We are studying the equilibrium of materials, the equilibrium state, which is equilibrium because it has the minimum energy. Well, of course, this minimum energy depends on the conditions, temperature, pressure, concentrations, etc., etc., etc. We will see it in details later, but the point is that the state towards which any process is tending, it is dictated by the minimum energy. Point number one. Now, point number two, another course called Kinetics from Chemistry or Transport Phenomena from Physics deals with how the process is actually taking place. So we have a given state of the material, and then we have that imaginary equilibrium state in which the material will have its minimum energy. Another question is how the material goes virtually from this initial state to that final equilibrium state. And here we can find principles that the mechanism or the processes also select paths with the least effort, or in other words, they just go against the least resistivity. Or we can say that they choose paths with the lowest activation energy. We can say that processes follow the principle of minimum spent energy. And now we can, of course, summarize or combine the two, and we can say that both the equilibrium state and the mechanisms to reach it are dictated by the same principle of minimum energy. Let me show to you this beautiful little river not so far from the city of Miskolc, and I want to show to you the equilibrium state and the mechanism how this river is trying to reach the equilibrium state. I hope you can see from the photograph that the top of the hill is here and the bottom of the hill or the direction towards the ocean is here. Well, of course, oceans are quite far from Miskolc, but nevertheless, water will reach it within a couple of weeks, maybe. The point is that, as you see, water is flowing from the top towards the bottom. Why? Because water follows the principle of the minimum potential energy. For water as a mechanical object, the equilibrium state is the place with the minimum potential energy, and is the place which is closest to the center of gravity of the Earth. Okay? So this is the analog of our chemical principle of equilibrium state of materials. Now, let me show to you how water does it. So water should flow, but water is not stupid. Chemical reactions are also not stupid. Water flows against the least resistivity. There are certain stones, like here, which are just overflown by water. There are some other stones here which are jumped over by the water. But there are bigger stones, and they are flown around by the water. So water flows as a mechanism according to the principle of minimum spent energy. You see the same principle in chemistry, in physics, in mechanics, everywhere. Even in social sciences, by the way, we can identify the goals of people by the minimum energy, because minimum energy is what they want most. Some of them wants to be the richest. Some of them wants to be the most beautiful. Some of them wants to be the strongest. Some of them wants to be the most influential. Whatever. And then, how does people reach their goals? Well, look here. There are certain obstacles on their way which they just overflow or jump over, and if the obstacle is too large, which stands on their way towards their goal, they just overflow. So people also act according to the principle that they flow against the least resistivity to reach their goals with the minimum energy. Okay, I hope you are happy with this double principle of minimum energy, but now let me come back to the number of base quantities. Well, I still think that the first step is to convince the SI bosses that we have 5 base quantities in nature, and that's why they should change the SI system, which claims that there are 7. But then we should also listen to my PhD student Adam Wake, who says maybe we have less than 5 base quantities. Saying the truth, I don't know any principle which says we must have exactly 7 base quantities, as the SI claims, or we must have exactly 5 base quantities, as Max Planck supposed, and I think today. So it might be 4, it might be 3, it might be 1. Of course, at the moment, I tell you the truth, I don't know how exactly we are going to deduce temperature from path and time. I mean length and time, but these are details. But now let me separate myself from those details, and generally speaking, the perfect state of natural philosophy would be to have a single final base quantity with single final base unit, with all other quantities and units following from these only single base quantity. Of course, there is lots of work to do to reach this state. If this state actually exists, I don't know, but I also cannot exclude so. And with my international students who are following me, please think about it. If you like, talk to Adam, especially if you are in Miskolc. It's very easy. But now it's time to finish this second lecture. Again, I can promise to you one thing. If I am still alive in these coronavirus times, I am coming back with the third lecture. Thank you so much. Goodbye.